Okay, so we start today the lecture. So we go back to our textbook. So because our homework one take a time, take a 2 week. So maybe our final exam will be delayed due to I have to finish the lecture before we have a final exam. So please do not forget to upload. So upload your homework one to eCourse. So you have to upload your homework one presentation file, just presentation file. So you have to upload it. So we go back to our lecture. So homework 2 I'll be give you in this week. Homework 2 will be just follow your homework 1 further. So homework 2 will be a little bit related to program. So you can simplify the algorithm what you read in the paper in homework 1. So due to our course lecture, so maybe our final exam will be a little bit delayed. So I'll do my best to finish what I need to talk in this semester. Okay, so let's start today the lecture. Today the lecture here. So let me check. Wait a minute. Okay, so first issue, we go back to see what we have. So first one, you can see our PowerPoint here. Is like our textbook here. I just briefly review what we talked in the previous lecture. First one, what's the source filter model? Source filter model is more like a we have like a impulse. If you have a voice, so you look like have a sound impulse stream. This one related to your pitch, and if on voice more related like a noise. So so you can see here. Let me double check it because not too many students on the line. So I make sure to do I announce the link. Okay. Okay, sure. Okay, so supposed to be I already announced it, so you can see today the link. Okay, so we have a source filter model. So right now it looks like you have a voice related like some periodical pulse, and if on voice more related on noise. So go through your something like a vocal track and go through your maybe like a gain. So you have a time variant. So this one related to your vocal track this one from your grotto. So this one you can see we have we model it like a LPC coefficient. So finally we come out the output speech. So this one is our best idea. And then you can see here, so we have like a because we try to model this transfer function. We have an output and we have a trigger input here. So we try to model it. So we have a transfer function. This one from your digital signal processing. Most of them we are defined. So we have a zero, we have a pole. So you can be general term like this one. So based on this equation, however, we try to simplify our transfer function. We assume the number, the order of denominator, in your denominator, the polynomial function, the order is higher than the order in numerator. So we can see if the order is higher than that. So we can say we can simplify that. So if our our transfer function is an open model, so we can do can reformulate the equation to become our trigger signal multiplied by gain, and then previous signal they have some linear combination to become the new signal. So this one become we are basic source filter model like this one. So later on you can see we try to find the coefficient here. So we assume this signal maybe is very small, maybe it's very small. So we try to minimize this one, approximate by this one. So we try to calculate the error function. So this one current speech signal depend on your previous signal. Try to do the linear combination. So this is our error function here. So we try to minimize the error function. So undetermined like a unknown parameter is our alpha. So we take a partial derivative. So we have a p unknown p parameter. Total is number of p. So we take a partial parameter. So because this one is second order, so they have the minima value. So if we are take the partial according your unknown parameter, we take the partial derivative, so they equal to 0, so they can get the minima error value. So we can say finally we come out like this kind of equation. So after we get this kind of equation, so you can see what we have. We try to solve this equation, so you can see it's more like a we try to get the alpha I. So we try to see correlation. So one correlation is like your respected to your index 0. The other one is try to do the neighboring correlation. So based on this one, so we can come out like a three method to solve this problem. So one is called the autocorrelation method, the other is covariance method, and later on we talking about lattice method. So for example, we try to get this one is more like a correlation. So correlation, autocorrelation, so it's more like a correlation. So they have, if we are consider the boundary condition, different boundary condition, so they will become out like this kind of equation. So you can see here, we try, if we are consider different boundary condition, so your information can be come out like this kind of metric. Why? So we can see last page here. Next page here, we are trying to from your partial derivative, so we can get a equation like this one, and then we try to find out your correlation, like a cross correlation and cross correlation. So we try to find out your phi. So you can see if we are consider the boundary condition like this one, we are not because you are reach the boundary, so we are not look forward. So you can see if we are like this one, and then we can calculate how the information, you can see it will be expanding like this one. So this one, because we can become the metric, try to solve the metric. So you try to get R1, R2 up to the RP here. So how to solve it? Because this one, they have some characteristics, some spatial feature. You can see diagonal are the same, and also corresponding the coordinate index try to interchange. So you can see they have the same value, corresponding position, so they have the same value. So more like a little bit symmetric metric. So they are symmetric metric. So we can sub this kind of symmetric metric. So we are call this one is a Toy-Place matrix. So in the mathematics, they have some like a iterative solving the problem. They call the Durbin algorithm. So it's more like a recursive to solve the solution. Sometimes you have to be careful, make sure they are not singular. So you can say based on iterative, so we can get the final result. So you have an unknown coefficient here, and then in the textbook they give you order to simplify the example, and then you to derive it again, and then finally, so this one is from your high school mathematics. Is very easy. Try to find inverse matrix. So you try to find their value in the and then reverse try to find a reverse metric. So according iterative and according your high school mathematics, you can find out the result are the same. So this one we call the autocorrelation method to solve your problem. So this one, why we say right now we try to solve the short-term prediction. That one is a LPC analysis. So we try to, what we want to do here, first issue is a source filter model. So what's the source filter model? So we have a source, we call this one is source filter model. So source filter model, we have first one, if you are voice, so we are periodical could be similar periodical path is like a trigger signal. And then on voice will be more like a noise here. So you will have some spatial gain here, and then we call this one is your vocal track. Maybe this one is your short-term prediction is an LPC model here. So and then you have an output here. So this one is just a source filter model. So in our equation here, so you can see they try to minimize first one because we have a speech signal, original speech signal. How to do it? So we try to partition speech frame. So we try to partition speech frame for speech frame, for example, is 10 milliseconds. So we are 8 kilohertz sampling rate. So you have an A sample here. So based on A sample here, we try to find your LPC coefficient, and also we try to find your pitch. So what's the pitch here? So maybe the pitch is look like this one is your pitch. So it's your pitch, and then this one is your signal pitch. And then also what's the LPC? LPC indicate, for example, this point will be using their neighboring signal to do the linear interpolation. So they will be according their neighboring signal to do the linear combination to predict this point. So we call the linear prediction coding. So here the P is, what's the P here? P is, you can see the P is try to look forward how many points to do the prediction. Look forward point. So the number of look forward the point. So you can see, because for this speech frame, so we try to find according our model. So in the beginning, so you can see in the beginning what we have. So in the beginning, they try to minimize the error function. So you have each signal try to minimize this one. So what's the minimize? So they try to using previous peak point peak signal to in linear prediction current signal. So we try to minimize this error. So we're using the mean square error, and later on we come out the cost function, the equation like this one. So this one, so you can see here, if we are looking into here, so your I is equal 1 to P. So if you are looking into here, so they will become out according. So this one, what's this one? This one will be considered. This one will be considered like this. For example, 80 sample. So they will be calculated according your speech frame 80 sample. So they try to calculate the correlation. And then find out the value. So let me take a little bit break and double check. Can you see it or not? Anyone can voice me? Did you on the line? I see one person on the line. So could you voice out? Send me the text and calculate the correlation. So you can see here, this one will be come out like this one, R1, R2, up to the RP here, and then you can have a matrix. So this matrix will be 0, 0, and 0, 1. So you can see they will become out your matrix like this one. So they call this one is Rn. So we didn't write it down. So they have some this matrix have some spatial conditions. So you can see they have Rn 1 and 2 and up to the Rnp. So this matrix will be diagonal, will be the same, and also corresponding component position, they are the same. So this matrix is symmetric matrix. So we call this matrix, so they are a Toy-Place matrix. So they can use in the Derby method. So they can use in the Derby method to solve this problem. So they can use in the Derby method. So it's more like an iterative. Why? Because popular use the order P, most of P order could be A or 10 or 12. So this matrix is very big. So if we are trying to find their inverse, it's not so straightforward. So you have to decompose their dimension and step by step. So it's not so straightforward. So we have using iterative to approximate and finally to get the result. So you can see this one because LPC linear prediction coding. So the main idea is based on your speech frame, based on speech frame here. Inside the speech frame, based on your signal correlation, and find out the best coefficient. So try to find out your best coefficient. Based on this coefficient you are using, based on this coefficient what you have, and then if each point using this kind of coefficient to do the linear combination, so they have, I'm missing here, so they are doing the linear combination, their total loss will be minimized. So the main idea here, they try to find according your speech frame, inside the speech frame, and then try to find which what kind of coefficient can do the good prediction. So right now if P is equal to 10, each sample look forward 10 sample, based on previous 10 sample to do the linear combination. And then the linear combination, the coefficient is this R is our linear coefficient here. So you can see we try to find max the minima. So each point is not just one point. Each point inside the frame. However, in the boundary, we are not over the boundary. So you can see here they have some condition here. They do not over the boundary, so they have a condition here. Sorry. So they try to find correlation equation. So they have try to think about the boundary. So they do not look out the boundary condition and make sure the signal inside the boundary. So you can see inside your frame. So your autocorrelation function will be find out. So the metric will become like this one. So they are symmetric metric and easy to solve it. However, the other one also to solve this kind of inverse metric problem, they call the covariance method. So covariance method, so they are consider the boundary maybe a little bit over your boundary. So you can see they are not trying to a little bit over. So that one is not a little bit not symmetric. So your common equation will be like this one. So your diagonal is not a perfect the same. Only corresponding point could be a little bit different. So this one, the straightforward, so is not a perfect symmetric. That one is called covariance metric. So Ij is Nji, so they a little bit same, but the diagonal is not the same. So they call this one, they are using, it's not a Durbin method, they're using the Cholesky decomposition to do this word. So they call the covariance method. So they also using the iterative, also using some methodology to do it. The other one try to solve your inverse metric. So the other one try to solve this inverse metric using different way. They call the lattice method. So lattice method, because in the autocorrelation and covariance, they are based on we have calculate correlation metric. So we try to find out autocorrelation value metric, and then correlation value, and then come out the metric first, and then we try to solve your inverse metric, and then try to find, because right now you have a matrix here, and then we try to get the R1, R2, Rp. So we try to get it, for example, this one is A. So we try to find out A inverse and A inverse here. So we can get R1, R2, Rp become A inverse, multiply this vector and can get the result. So the method here, like a autocorrelation method and covariance method, they try to find inverse metric. However, because if we consider the boundary condition different and make the metric, one metric is symmetric metric, the other one is covariance metric. So in different conditions, so they will be using different way to solve the inverse metric. So another one, they are not trying to formulate this equation. So you can see previous two methods, they are using common correlation value metric first, and then they try to solve the problem. And however, right now they say maybe we can combine them or using different ways. They call the lattice method. So they combine two steps and compute the LPC parameter. So we are not dig into the equation here. So this one just tell you they have the other approach to do. They call the lattice method. So right now we have one is called autocorrelation, the other is covariance method, and that's one they call the lattice. But the lattice is combine what we did. They try to generate metric and inverse the metric. They combine them together, so they come out like called the lattice method. So we are not go through the equation. So most of popular use, because we try to simplify the computation complexity. Most of standard they are using the autocorrelation method, using symmetric metric to solve the equation. Try to find your short-term prediction, short-term coefficient. So this one is your linear prediction coefficient. So this main idea. So the first one, because speech processing, we try because the speech compression is more like a model-based encoding. So however, they cannot wait for your long talk. So they will be partition your speech waveform into many speech frame. Based on each speech frame, they are try to find some parameter, some feature. So first feature they call the linear prediction coding. So linear prediction coding, they try to inside the speech frame, each signal will be based on look forward p sample to do the linear combination to predict your current sample. So because inside this speech frame they using the same coefficient, so they try to what kind of coefficient can make the estimation prediction loss, prediction error big small, minimize the prediction error. So we come out the equation become the inverse metric. So however, we have three methods. One we call autocorrelation method. The other one is a lattice covariance method. Autocorrelation and covariance method, they are focused try to come out inverse metric using iterative method, iterative procedure. They using iterative procedure to come out the result. And then the other one they call the lattice method. So lattice method, they are focused on they combine two methods. One, during you generate the metric and also try to solve the inverse. They combine them together. So right now we are not focused that one. So you have to know right now. Try to solve your linear prediction coding coefficient. Try to get your linear prediction coefficient. They have a three method mentioned in your textbook. But most of a popular use method are the first one. They call the autocorrelation method. Okay, I'm using the Mandarin to repeat what I talk here. Is short-term prediction. 好，那我简单讲一下哈。实际上，这整个概念呢，实际上就是 source filter model。那 source filter model 呢，我们为了要去做一件事情，实际上就是把 waveform 呢切了很多音框。那每个音框在这个音框里面呢，我要想办法找出它的压缩可能的 model 的参数。那我们称作 source filter model， 实际上就是按照人类的口腔的机制。可能你的喉门的 pitch pitch 的开关，然后无声的时候就是代表像是有点 noise， 然后你的那个什么口腔就像有点像是 LPC， 然后当然你有能量的 gain 跟大小。那基本精神呢，就是说我现阶段这个 waveform 这个讯号，我在这个80个点，每一个点 每一个点每一个点都是用前面的 P 个点做线性预估，在这个音框它的线性预估的系数是固定的。那也就是说 P 如果是10，这10个系数是固定的，我到底要用在这个音框它10个系数是什么？那10个系数怎么去做预估？也就是说我只要将来有前面的10个点我就可以预估下一点，之后这整个音框所有点都可以被预估回来，因为我有一个让它预估误差最小的系数。那在解这个的时候，因为我的未知数是 R 化，那我有 P 个未知数，我对它做偏微分，因为这 R 化是2次4，所以说偏微分等于0是极小值。那最后呢，你就会发觉我把它推完之后，它会等于这个式子。那这个式子如果把它展开呢，实际上就是有一个矩阵乘上你的未知数，那右边是一个 vector。那这些内容呢，刚好都是算出来都是 correlation， 也就是说它们之间的那个讯号移位跟移位差多少，一个是不动，一个移位，那一个是移 I， 一个是移 J， 它们之间的关系。那因为我在移位算 correlation， 如果对 boundary 的处理，有时候会跨 boundary， 因为我的音框还在，内容还在，那我并没有把外面。如果跨 boundary 的处理不一样，会造成你的矩阵呢是对称或不对称一个是原则上是上下一定是相似，但是呢中间的这个 diagonal 在 diagonal 如果往内说的话，中间 diagonal 是一致的，那或者是说你考虑的 boundary 不一样，中间 diagonal 是不一样，那不一样的是用 covariance 的方法那它是 covariance metric， 它是用 covariance 来解它的方法。那另外一个呢，对角线一样，那我就是用 autocorrelation 的方法，实际上它是一个迭代方式来算因为它的维度 P 呢通常不小，我不会是直接去算反矩阵反矩阵通常会有一个问题，就是说我怕它的这个矩阵的那个 determine 值会接近0那相对会出现问题，那就会 singular 的问题。那所以说呢，我们就是用迭代那但是另外一个方法叫 lattice， 因为你可以发觉前面所推到现在，第一步呢我是建构出这个条件，这个条件的展开是一个矩阵乘上 vector 等于 vector， 那我的未知数都在这里，我只要求出反矩阵就可以。那另外一个 lattice 方法是说，在你建构这个预估的过程，我实际上就没有所谓建构2阶算，就建构过程跟求解合并在一起，那这个叫做 lattice 方法。那某种程度我们在这边不讨论细节数学，那基本精神你要知道的是我们在做 LPC， 实际上它叫做 short-term prediction， 短时域的一个预估。为什么？因为它本身就是考虑临近点做线性预估，那这个音框里面所有线性预估的系数是一样的，那到底是哪些的线性预估系数可以让整体误差最小，这就是我要看的东西。Okay, so you can see here if we are implement LPC, so they have some condition you have to understand. Okay, so in practical implementation your LPC analysis, so they have several important factor you have to consider. First one, they will be consider your performance and also efficiency. Sometimes stability you have to consider. So lattice method used to be could be preferred in real time, but guarantee stability. Sometimes they guarantee stability, but careful if you consider careful choice your windowing and also fine precision arithmetic. So sometimes autocorrelation method and covariance method are equivalent to your lattice method for stability because they have an inverse metric to do the calculation. So if we are consider quantization to the coefficient, sometimes stability would be maintained to some extent. So they have some stability check during your decoding. So the second group involve a choice how to choose your order P. What's the P will be the good order. So another one, your analysis frame. So in the past, we're talking about the windowing. So the number of n number of frame size depend on they hope to cover one of two or three pitch. So most of them consider because our pitch human being pitch is around from the 18 sample to the 160. So human being pitch number pitch period according to your textbook, the human being pitch is around the 18 to 116 sample. So most of them, so you can see under 8 kilohertz sampling rate, So our N speech frame, most of them 10 millisecond to 30 millisecond, most popular use. So this one is 80 sample, 240 sample. Because your sample is bigger, sometimes your end-to-end delay, so your end-to-end delay will be increased. So will be consider low delay. So sometimes will be prefer n become smaller, but your n smaller, so your compression ratio maybe cannot be do the good job. So compression ratio also become lower, because if you are n bigger and make your higher compression ratio, once your n becomes smaller, so sometimes it's not easy to improve your compression ratio. So you can see have some trade-off here. However, because we are model based, we try to model your speech, so we hope to your speech frame to cover a pitch information. You hope to cover the pitch information. So most of them standard using the 80 to up to the 240 sample for per one speech frame. So you can see here they show you one figure here. They show you one figure here. So you can see if we are consider they are close to pitch gain saturation, so they cannot improve the pitch gain. So sometimes you using a lot of a number, using a lot of previous sample to do the prediction. The order become bigger. Sometimes you cannot get a lot of a pitch gain. So you can see you have to do some trade-off, because a lot of order will be have some the other problem. Because like here, if we are p equal to 10, so you can see this vector is 10, and how about this metric? This metric will become 10 by 10. So you have to calculate 10 by 10 metric inverse. If we have p become 20, so this vector become 20, so your metric become 20 by 20. So the computation complexity is increased. So we are trying to try off it. So you can see the filter order supposed to be from your pitch gain, so the minima should be like an A, so they can get a reasonable performance. So usually they are using 10 pole, so 10 number of 10, p equal to 10 to do the prediction. So consider your formal resonances, because they are general spectrum shape. So why? Because if you are consider they are according your speech frame. So we have a speech frame. So you have a signal. like this one, and then go to your frequency domain, so they will be like this one. So they try to find the envelope shape. They try to find the envelope shape. So this one is your Foreman 1, this one will be your Foreman 2, this one is your Foreman 3, this one is your Foreman 4. So we try, because sometimes you try to catch the meaning, what you say, linguistic meaning. So we have to, because they have a four dominant important information, try to understand what you pronounce, like R, E, U, A, for example, like this kind of phony. So because you try to model this one, so you have a 4 peak, so your P order equal to A, so should be bigger than A, more like a sample series. So our order become A, so we can see you have a four turn here. So if we have frequency like a 4, so we are sample frequency should be A, bigger than A, because in our frequency domain, from the envelope shape, we call this one is envelope shape. Envelope shape. We try to know what's the performance you have. So they consider 10 order filter use, so the Foreman resonances and general spectrum shape is model. So this one they call general spectrum shape, and then this one is a Foreman. So fundamental frequency, you have to distinguish. One we call the fundamental frequency. Fundamental frequency they call the F0. So this one is your pitch, inverse your pitch. So inverse your pitch. So fundamental frequency from here, maybe I draw is not so clear. So it's more like some harmonic. So this one is your fundamental frequency. But F1, F2, F3, F4, this one is your frequency waveform envelope shape, your envelope shape peak point. So they are approximate come out 4 peak point. Based on 4 peak point, you are sample 4 peak point. So your sample order should be bigger than 8. So used to be, we are trying to using 10 pole. So 10 pole to do it. Okay. So however, much higher order sometimes complexity will be higher. However, there one standard, they are using high order. This one is more like a low delay standard. So they are using high order to do it. So however, they did not consider the pitch in their standard. So LPG filter prediction gain. So you can see here what we get. So it's bigger than 10 is reasonable. So also you can see the frame size that here they're talking about 16 to 32 milliseconds. So most of them standard could be using 10 to 30. So we are trying to see sometime we are consider reduce the effect window position, some common preprocessing. So they will be considered little bit overlapping window frame. Overlapping frame try to overcome some blocking edge. So could be 10 to 20% frame size overlap. So however, in speech frame, speech coding, they are not popular use overlapping, because if you remember what we did before, we try to do the windowing original signal. If you have an original signal, we try to use in Hamming window. So this one could be your one speech frame, could be like a 20 millisecond. So you are using Hamming window. Hamming window, once you come out, from after Hamming window, when you come out here, so they will be make the boundary signal become smaller, and then keep it in the middle, and in the boundary become smaller. So the boundary effect become minimized. However, your boundary information a little bit missing. So we try to base on your complete information in center to build out the model. So we are trying to smooth it. So make this one close to 0 in the boundary. So your boundary try to become the 0. So this one sometimes speech coding, they will be considered next frame they have a 10%. This one could be 10% to 20% overlap. But sometimes speech coding they did not use it because during your recover, if your speech frame have an overlap, so you have a two sides come out the speech signal. So sometimes they have to figure out the overlap, how to process it. So maybe they did not consider most of the standard. Maybe they do not consider the overlap issue because two-way phone summation will be make your speech signal become not so clear. So you have to make sure how to mix them together. So speech coding, most of standard do not have overlap to overcome the blocking effect. So they don't care. They just using some smooth filter to do the work and make them they are continuous. That's it. That one will be straightforward and easy. So this figure just show you we have a speech signal. So you can see we have a speech signal in time domain, and later on they come out in frequency domain here. In frequency domain, so you can see they have some envelope shape. You can see they have an envelope shape here, envelope shape here, and envelope shape here. So our older A, so they a little bit model the envelope shape. Older P, they also model your envelope shape here. So if older is higher, they can model more detail, more detailed information. However, the model more detailed envelope shape may be not useful. Sometimes become some noise. So you can see what's the short-term prediction, LPC. LPC is the physical meaning. They try to model the speech signal, frame, they are frequency domain envelope shape. So you can see what's the LPC. The physical meaning is like they try to model your speech frame signal envelope shape. In frequency domains, they can model the envelope shape. So if we are original signal, we remove your LPC signal, so this kind become LPC residual. So if we have signal remove it, so you can see we still have some pitch signal over there. So later on, we are trying to model the pitch. Okay. So you can see this one is the original signal waveform, and then this one -9 is our LPC. So if we are original signal delete it. So we try to remove LPC inverse signal. So later on, you can residual signal go through frequency domain. There could be no envelope shape. They become harmonic. So you can see here this one in frequency domain like this one. So -9 is LPC waveform. Try to remove it. So in time domain become here, and then this signal goes through FFT Fourier transform. So you can see more like a harmonic. So later on we have LPC. So we consider maybe it's the pitch processing. So after LPC inverse filter, the result signal so could have a much lower spectrum variation. So than original signal. So you can see here. So LPC can view a method like a short time spectral estimation. So we can see like a frequency. So feature can be observed. LPC spectrum envelope match or signal spectrum much better than spectrum peak. So LPC more likely is likely model your envelope shape is so better than just individual spectrum peak. So you can expand model transfer function. So you can see our model transfer function h of z have pole only to model Foreman peak, no zero. So you can see once we see LPC, because we are open model, so you can see they try to model the peak point, not the zero. Zero will become to make this signal become lower, but they also model their peak. So this one, because we assume the open model, so later on, so you can see we are model signal envelope shape better than their value. So later on, after during the decoding, because we are open model, sometimes we try to do the other compensate, make the value become clear, make your speech signal to become enhanced. So here, what they want to say here, you have to remember, because they are trying to do the LPC. So we know how to calculate LPC signal, and later on we have to determine the order. So here we have to say, so because you have a speech signal here, and then speech friend, so you have a frequency domain, so you have a frequency domain here. So what your LPC try to model your envelope shape. So this one, what we model is your Foreman. What we model is your Foreman here. So is model your envelope shape. If your P order become the bigger, so they will be model more detailed. So suppose be like this one, P could be like a 10. So P equal to 10, so you model more like this one. So if P equal to 20, they will be modeled by this one, more detailed. So model more detailed. So like this one is model more detailed. But you can see our LPC, what we did derivation, equation formulation, they are based on open model. So they are open model, they are vary. This one is your vary. This one is your vary. So this one is your peak point. So peak point. So vary is not so clear. So some of the decoder, they post filter during the decoder, they will have some post filter to make them more sharp. And based on post-processing can make the speech signal more clear. So because we are open model. So another issue here, because original signal we model, we find out LPC signal. So we are synthesis back because synthesis is the waveform. LPC synthesis is the waveform. So you have a synthesis signal. So they are do the subtraction signal from original signal, because you are synthesize, because you get a LPC coefficient, you synthesize, become the signal, try to subtraction each other, become the remaining signal. Residual, they call the residual signal. So residual signal, so go through frequency domain. So they are no envelope shape. So based on this one, we try to find their harmonic. try to find the fundamental frequency. This one we call the pitch. Okay, are you using the Mandarin? Repeat again. 我们刚才讲了3个方法找到了LPC 的系数。那接下来你要看的是 LPC 系数的 order 要用谁会好那如果我的 order 越多，实际上我的 pitch gain 呢并没有增加很多。那我或许说我 pitch gain 呢不需要那么order 不用那么高，因为高的话你的那个反矩阵求解本来 P 是10，你的是10乘10的矩阵反矩阵求解。那如果你的 P 是20，你就要求20乘20的反矩阵求解，相对复杂度就蛮高的。那而且 pitch 我要的 pitch gain 误差也没有增加很多。那从以前的语言学在辨识语义内容，主要的精神是form。Form 1, Form 2, Form 3, Form 4， 因为 R、E、U、L、O 这些母音子音有时候是帮忙辨识，但是母音为主。那它的母音 F1、F2、F3、F4 分布的地方都不一样。那实际上这些 pick 点不一样，人类实际上是已经可以分辨语义的内容。所以语音压缩的第一个基本精神就是语义要保持，否则的话它不会抓到重点。好，那我既然 envelope shape 在 P 等于10的时候已经抓到了，我根本不需要去，所以说你 P 等于10，某种程度 envelope shape 已经抓到，那我的细节呢可能就不需要去包含那么多细节，那复杂度反而变大，有时候会影响到我的压缩的效果。那因为 O 的多了，那我要纯压缩就变多。那如果我把原来的讯号我找到 LPC order 的系数了，那我把它合成 waveform， 那原始讯号跟我合成讯号相减，就剩下剩余讯号。那我也就是说原始讯号减掉 LPC 讯号合成讯号，我就剩下 LPC 的剩余信号。那剩余信号呢，如果你到频谱去看呢，它的 envelope shape 便没有了，纯粹就是类似 harmonic 讯号。harmonic 讯号某种程度在时域轴是 pitch， 在频域轴就是这个基本的 harmonic 讯号。所以说呢，我知道了这个 harmonic 讯号呢，代表说我原来 LPC 呢实际上是在做一件事情，我语音压缩，我切了音框，音框的大小，每个音框大小需要包含1到2个 pitch， 然后接下来我避免 boundary 影响我的 modeling， 因为 boundary 它的周围讯号的资讯不全，当我做 model 的时候取参数会影响到，所以我用 Hamming window 把 boundary effect 变小， boundary 值变小，然后中间的值在我的 window 里中间值它前后的关系比较完整来建构模型。那我的 short term prediction 是我现在的点是用假设 P 等于10，用前面10个点线性预估我现在这一点，但是这个音框里面它的线性预估的系数都是同样的一个值，这10个系数都是固定的。那每个音框到底哪10个系数会是让它的预估的误差最小？那前面推出来就是反矩阵求解，就是类似矩阵求解。然后借由这样的一个做法，那我们就开始去分析我的 O 的数要多少。那 O 的数多少就跟你的语音，因为要辨识语义，那所以说它会跟你的 form 有关。那 form 有关 ，form 大概我们考虑到了 envelope shape 整个 envelope 频谱大概的 shape 我可以 model 接近4个，然后我就希望说 P 要大于8也就接近，一般来说是用到10不需要刚刚好。然后呢，你会发觉，当我把这个10阶的 LPC 系数找到了，接下来把原始讯号去掉 LPC 的合成讯号，剩下讯号我再去频率 domain 看，它的 envelope shape 就没有了，就剩下什么呢？就剩下接近 harmonic shape， 当然还有其他成分，那个成分目前还不容易做 model。好， 然后其次的话 LPC 呢某种程度它就实际上物理意义是 envelope shape。好，那因为呢我是 OPPO model 是 model 什么？因为它是在分母，所以讯号的波峰 model 的好，波谷 model 的不好。所以说在语音合成的时候，我们会做一件事情，去加强讯号的波谷，会加强讯号的波谷。在合成的时候，因为我已经都找到 LPC 了，那 decoder 的时候 based on 这个 LPC 系数的 model， 那我合成讯号的时候，我想办法去加强波谷，让我的讯号的效果就是清晰度变好，大概会是这样。OK。So this one just LPC. So LPC is very easy. So we call this one is short-term prediction because they are based on your previous neighboring signal do the prediction. So P is look forward the number of sample. So how many number of look forward sample? So is equal to P. So P become the 10, we look forward 10 sample to do the linear combination. So to predict the current sample. So for each speech frame, we only have a pair, only have a set of order. So like we have a 10 coefficient prediction a linear prediction coefficient. So in this speech frame, we only fix this 10 is a fixed value. So how to find the best 10 coefficient for this speech frame? So we come out is like an inverse metric. So inverse metric. So maybe they using the autocorrelation method, covariance method. Even you are using lattice method. So however, you have to look into how to determine the number of order P. So number of order P depend on how do you model, how detail your envelope shape. Because we are OPPO model, so we model signal peak will be more clear, valley is not so clear. So we are model envelope shape. So because traditional, we are trying to recognize linguistic information. Most of them based on 4 format. So P bigger than A is good enough, like a sample series. We have a 4 point. So we are sample it like become bigger than A. So in standard, most of standard are to use that P equal to 10. So you have to know this one we call the short-term prediction. Short-term prediction main idea try to model your signal spectrum wave spectrum envelope, and then if you remove LPC synthesized signal, later on your signal become related to harmonic, more like harmonic, no envelope shape. So if you remove speech signal, remove LPC signal, so original signal remove synthesized LPC signal become the residual signal. If you are looking into the residual signal in frequency domain, they are envelope more like a harmonic signal, no envelope shape, no this one envelope shape. So they are cup of envelope shape become so the envelope shape will be removed, so they will become like a harmonic here. So this one you have to know what's the physical meaning here. So later on, so right now on next one we are talking about the pitch. So we already find out the LPC coefficient. So we have to find out what's the pitch signal. So the easy way, we are trying to remove the LPC impact, because we can pass on original signal to find the pitch. Also, we can find the pitch, remove LPC, because if you are considered like this one, so when we draw like this one with original signal in frequency domain could be like this one, and then original signal remove LPC signal, their frequency domain could be like this one. So right now we have to find out their harmonic. What's the harmonic? Harmonic signal is more like this one. We call the F0. So suppose be their F0 could be closely. So harmonic. So if we have an envelope shape signal, try to find out, there will be bias affected by your envelope shape. If the signal without the envelope shape, you try to find their fundamental frequency can be get more precisely precisely data. So we are prefer consider a residual signal to do the pitch prediction. So because the pitch prediction, so you can see our short-term prediction called linear prediction coding. They are based on neighboring signal do linear combination to do the prediction. Pitch prediction will be considered maybe 30 sample, 60 sample to do the prediction. They move to here using their neighboring sample to do the linear prediction here, or just using one sample to predict there. So there will have some gain there. So you can see pitch prediction will be take a longer step to do the prediction. So we call this one is a long-term prediction. This one we call the long-term prediction. So LPC we call this one is a short-term prediction. So because they are closely to do the prediction, so they are neighboring to do the prediction, a previous sample to do the prediction, we call the short-term prediction. So you can see the long-term prediction correlation. So they are during the voice, they're still between the sample. So sometimes you can see sharp periodical. So we try to find some periodical signal over there. So that one could be easy for us to model it. So you can see maybe one more pitch away. So they call the long-term prediction. Okay. So long-term prediction, if we are trying to consider, they can be modeled by this equation. Why? So what's this meaning? They are trying to look forward t step and using neighboring I. What's this equation meaning here? That one is more like a signal. So they are moved to t, and then this sample using this sample, and also neighboring pixel to do the prediction. So if I equal to 2, so you are using 5 sample. So you have a 5 sample to do the combination, linear combination. So it's a linear combination to do the prediction. So you'll be to do the linear you have a 5 sample to do the prediction. So this one equation. So you look like you are look backward t sample around that point neighboring 2i plus 1. So it's a 2i plus 1 point to do linear prediction. So you can see T is your pitch, Vi, so this Vi is your pitch gain. So if your pitch gain here, so you can see we have LPC. We already get LPC. So we try to think about how to generate a pitch filter. So this one is your trigger signal. So we have a trigger signal, and then we are consider this one based on your synthesized signal. So this one we assume they are based on residual signal. The signal removed, so the past excitation, so it's LPC residual signal. So we are residual signal because this one is synthesized signal. Synthesized signal compare original signal, they have a difference. The difference is the residual signal. So residual signal, based on residual signal, we try to find your long-term prediction. So however, here the tau, because right now, because your short-term prediction, your unknown parameter only your coefficient AZ. Long-term prediction, your unknown parameter, you have a BZ and T. So you have to be careful how to determine tau and beta. So they have a one-shot optimization or iterative sequential approach to find out how to get a good result for that. So this one is our first part, and second part I'll be looking to how to get the result, how to calculate a long-term prediction for your pitch information. Okay, so we stop here, and 15 minutes later, so 15 minutes later will be like a 55. So 40 right now is around 40. So before 55, before 4:55, so we'll be start second lecture. Okay, we stop here.